OK.
Yes.
Donc, bienvenue au séminaire d'informatique cognitive. Cette fois-ci, on a Lorenzo NATALE de Genoa. Il est chercheur principal à l'Institut italien de technologie et coordinateur au Centre de robotique et de systèmes intelligents. Il a été l'un des principaux contributeurs à la conception et au développement du robot humanoïde iCub. How do you pronounce it? iCub? iCub?
iCub.
Le robot iCub. Ses intérêts de recherche portent sur la vision artificielle, la perception tactile et les architectures logicielles pour la robotique. Cette conférence présentera le système sensoriel que Lorenzo a développé pour le robot humanoïde iCub et en particulier la technologie de détection tactile. Il discutera la façon d'utiliser la rétroaction visuelle et tactile pour explorer des objets inconnus et contrôler l'interaction entre la main et les objets pour la modélisation de formes, la discrimination d'objets et le suivi. Enfin, des travaux récents seront rapportés concernant les algorithmes d'apprentissage rapide pour la segmentation d'objets. Cela s'appuie sur l'interaction avec un enseignant et l'apprentissage actif pour l'adaptation de nouveaux contextes. With that, I hand over. Oh yes, I have to explain also. Il faut que j'explique aussi que les questions se posent dans le chat et moi je vais passer les questions à Monsieur Natale après. Lorenzo, it's yours.
Thank you very much. So let me share the screen. And okay, can you see it?
Yep, it's fine.
Okay, so thank you very much for having me today here. So I will talk about some of our work in our lab concerning integration, the use of different modality, vision and touch, and some work on integration of the two for object recognition and object manipulation. And in particular, experiments we have been doing with the iCub humanoid robot. Just in a short slide, what we do in my group, I am the responsible leader of a group called Humanoid Sensing and Perception. And what we do is basically we work on perception for using visual information, visual feedback, control of the interaction between the robot and the environment through navigation and through object manipulation. And the idea is that this is a loop where you start from visual perception and through interaction, you get some tactile perception and you can learn out of this loop better perception through interaction. And because we do a lot of work that integrates together different algorithms, different components, we also need to develop the robots that we use, but also the software tools that we need for integrating several components together to build complex behavior. So I want to start with a general introduction on the problem that we have in robotics. And as you probably know, there's been this machine learning revolution where today data-driven methods in general have had a big impact on how machines perceive the environment through vision, language processing, and also control. This work here is one of the most popular, maybe from OpenAI, where they solved a complex manipulation problem in simulation. But the general trend of this approach is there's big assumptions underneath. And the main assumption is that there's a huge data available for the learning. And this data can be real or synthetic. And also computation is free. You have huge amount of computation available. Supervision is free, or not free, but it's given for granted from humans. A lot of humans that are usually involved in selecting data sets for the AI systems. And learning, this is also important because of all these reasons. Learning is typically performed offline, and that is then deployed on the robots, but there's little adaptation online. And this is for robotics a big limitations that is preventing some of the advantages. Of course, still all these algorithms are useful in robotics, but a lot of the advantages are still not getting to robotics because there are some problems. So for example, how do we get sufficient amount of data if the robot needs to learn something on his own without the help of humans? And then where do we get supervision for supervised algorithms? How to explore safely the environment in the real environment. In simulation, you can fail, but if the robot fails in the real world, then failures can be catastrophic. And then, as I said before, there's need to adapt and learn online. And if you look at, and this is what inspired some of my work, if you look at how humans, on the other hand, learn, we learn a lot from integration of multiple modalities, touch, vision, proprioception. We are active systems, so we actively probe the environment to extract information. This example, I hope it plays. There's a couple of videos here. Okay, they're not working, but anyway. So we interact with the objects to extract information through touch, but also through vision, and this allows us to extract better data than data that will not be available. For example, the tactile information will not be available without touch, but also vision. We get better data because we can actively control how we extract information from the environment, and this information is not completely random, but is structured because of the physical interaction. So a structure means structure in space and in time. And this can also be leveraged for simplifying the control and the learning problem. Okay, so these are not probably the videos. Okay, so the outline of my talk, I will briefly present the iCub and the tactile system that we developed for the iCub. As I was saying during the introduction, tactile systems are not something that are very easy to get in robots, so we had to work a lot to get good tactile sensors. And then I will present 3 blocks of work that I divided roughly in learning about the body, where the robot has to learn about his own body, then learning about object through vision, and then learning about object through touch. So the sensory system of the robot is exemplified here. There is an inertial sensor on the head, visual sensors on the eyes, force sensors in the shoulders of the robot, and the tactile skin distributed on the whole body of the robot and the fingertips. And then we also got inertial sensors in the hands. These came for free because these sensors are so cheap that we could fit them into the tactile sensors, and for free we got also inertial sensors in the hand, which is not human anthropomorphic, but it was, as I said, something that we got almost for free. The tactile sensor, on the other hand, was something that we had to work a lot to get. And the challenge was that even if there were already some technologies for touch, for example, the capacitive technology was already available on the cell phones, for example, or some models of the cell phones. It was difficult to use the same technology as is on robots. The main reasons there were 2 main reasons. One is that the those tactile sensors were rigid. The technology was rigid and could not be deployed on non-flat surfaces like the body of the robot. And then we wanted a system that could cover large areas of the body of the robot, and not only a very small area. And for that, we needed to solve a sort of a system challenge, how to make a system that could scale to a large number of sensors and a large area. So the technology is, as I said, is a capacitive technology where you have 3 layers, basically. The first layer is an electrode, then you have a soft material in between, and then you have another layer, which is conductive. The 3 together, they form a capacitor. And the trick is that because the material is soft, the dielectric is soft, when you push the capacitor, you modify the capacitance because you change the distance between the 2 conductive plates. And if you measure the capacity, you measure variation in the capacity, you get an estimation of the pressure that is applied to the sensor.
Lorenzo, excuse me.
Yes?
Did you say, maybe you said already, did you embed this in all of the skin on the robot or only on one hand regions?
No, in the whole body. I will show you in.
With the same sensitivity everywhere?
No, not on the. We had basically two different sensitivity,
okay.
Fingertips and the rest of the body.
Okay, I understand. Thank you.
So the layer, the system is made through a flexible PCB that the elements are triangles, and each triangle has 10 sensors. And on the back of the triangle, there is a small chip that is reading the capacitance, but is also able to talk to the other triangles in a network. So the main idea here is that when you have you can from one triangle you can read the values of the other triangle. So there is a network of triangles that can communicate, and this reduces the number of wires that you need in the skin, because you can read from one triangle all the information from the other triangles. And the other thing is that the PCB is flexible, so it can be flexed a lot, especially at between triangles. It can also bend, not too much, but it can bend significantly also as in itself, the triangle itself. So by deploying it, when you design a patch that you want to use to cover one part of the robot, you can have like an hexagon, and then by cutting through the hexagon, you can extract a patch, and this patch can be then deployed on the robot and work as a capacitor, as a tactile sensor. This is an example of the sensitivity of the system on the bench. This is not mounted on the robot. When we did this experiment, basically this shows the response of each tactile, 1, 2, 3, 4, up to 5, up to 8. When you put a constant pressure on the sensor, and you see that you get nice receptive fields in a way that are maximally activated when the sensor is pushed on the top, on the tip, and then the response decays when you move away. This is due to the fact that the soft material distributes the pressure, and then the other sensor get activated when you move the probe. And this shows the sensitivity in pressure in kilopascal. Just pushing one sensor at the top where it's maximally sensitive. This is the type of sensitivity you can achieve on the triangles. This shows what type of information you can get when you push the robot, and shows also the deployment of the skin on the robot. As you can see, we cover the torso of the robot, the arms, the forearm, and the arm, and the hand with the same technology. And the first way you can use this sensor, for example, is to detect contact and to control the robot so that it moves away the arm when there is a contact. So it's a sort of avoidance of contacts, which allows the robot to be compliant to contact, or in case it's actually moving, to stop and avoid to break objects around when it's touching. And the fact that it's a whole body system is useful because the robot can interact not only with the hands, but also with the whole body when it's moving in the environment, either because there are humans around or because it's moving in the environment. On the back, you see also a representation of the skin with the red that shows when the robot is touched, when the tactile sensors are activated. This is a customization of the same technology on the fingertip and on the hand. It's still a sandwich capacitor, but the layout is different. The triangles were too large for the hand, so we ended up developing a new system that you see for the palm here, and for the fingertip we had to change completely. There's still a flexible PCB that is wrapped around a fixed a plastic fingertip, and then there is an external layer that makes the electric and the conductive layer. This is an example of the type of control you can do with tactile sensors. These are objects that are not known to the robot, but just controlling the pressure on the fingertip. The robot is able to manipulate the objects and keep them in the hand without dropping them and without having a geometrical model of the object. Okay, so this leads to the first sort of chapter of my presentation, the first section. So learning about the body is exactly related to learning about the tactile system. If you know where you put the sensors, you know the position of the sensors, but you can also try to learn where each taxel is on the skin. This is not just a theoretical problem; it's also a practical one, because when you deploy the fingers, the tactile sensors, you don't know exactly how you place the sensors on the structure of the robot. There might be some small errors that you make when you glue it. So one of the questions we had was, can we calibrate the tactile system directly on the robot? And we found that the one possibility, there are two solutions that we proposed. The first one is to calibrate it using the force torque sensor that is on the shoulder. The force torque sensor is measuring the force and the torque in the shoulder. So if you assume that you push an object, or you touch the robot without producing torque, then you can use the estimated force and measure the torque to compute the displacement between the force torque sensor and the force on the tactile sensor here. So you measure the torque the moment that the force is doing, and if there are no other external moments acting on the robot, every time you push, you measure the force from the force torque sensor, you measure the torque, and then you can estimate the distance between the force torque sensor and the contact point. This is just a distance. It's basically an array, an axis. So you don't know exactly where the tactile sensor is along this axis, but if you push the sensor in different directions, you can compute different axes. And if you check for if you look for the intersection of several axes, then you get an estimation of the taxel. And in fact, this is what we got by pushing the robot several times and doing a sort of least square estimation, which is fairly okay approximation of the position of the tactile sensors in the robot upper body, in the arm, with an error of 7 or 6 millimeters. 7 millimeters is .2 if you just do pure estimation. If you then add the constraint that you know the surface of the skin, the shape of the robot without knowing exactly the position, then you constrain the sensors to stay on the surface, and you can lower a bit the estimation of the position, the error, to 6.6 millimeters on average. Another type of calibration, this is not my work actually, it's more work done by Alessandro Roncone, Mattei Hoffman, and Giorgio Metta. This was inspired by neuroscience, basically some neurons that are in the brain, and don't remember exactly which area, that are responsible for, they respond to either to vision or to touch when an object is approaching the body of a person. So inspired by these visual tactile neurons, they decided to attempt to simulate something similar. And in the end, what they did, they modeled a set of receptive fields on the tactile sensors, and they learned the response of the tactile sensor by looking at the same time when an object was approaching the robot, the direction of approach, and then given the direction on which part of the skin the object will impact, and then linking each tactile sensor to the direction of approach in the visual space. So basically, this allowed to build a sort of visual tactile representation of the skin. So it's no longer geometrical position in Cartesian space as before, but is directly in the visual space. So basically, what you can do later when you have done this learning, if an object is approaching the robot, you can anticipate where on the skin this object will impact. And you can use that for avoidance, for example. So here is an example during the training. You see that Alessandro is pushing an object. You see the red activation of the skin, and then the green is the estimation that is given by the system after learning. So the approach of the object is activating the tactile sensor that will be likely to be activated if the object will impact on the skin. And then this shows how you can use it for avoidance. So here you see the object is approaching. In green, you see the prediction of where the object will impact, and then the robot is trying to avoid by moving away before the contact happens. If it's fast enough, it manages to avoid the contact. Otherwise, then there was a red activation that meant that the object actually impacted the skin, and then it was a real contact. Another problem we had, this is not related to tactile to touch, but is related just to vision, is for the robot is to know where his own hand is, which might seem trivial, but for some manipulators that's not the case. In particular for humanoid robots that use many times tendons instead of gearboxes, it's difficult to model exactly the kinematic chain of the robot. In industrial robots, it is simpler because there is the robots are rigid. Humanoid robots sometimes, and especially the iCub, is elastic, small elasticity in the standards. So this is difficult to be modeled. So when you have a kinematics geometrical model of the robot, you have an error. And if you try to guess, to estimate where the hand is by using only notion of the position of the motors in the robot, you end up with a large error that you can see, for example, in this video. And if you want to control the hand to manipulate an object, these errors are catastrophic because they make the hand impact on the object. So an approach that works very well in robotics, if you know where the hand is in visual space, is very easy to control any point of the hand using take a reference point in the hand and control the arm so that this point in the hand goes exactly to touch another point, again, in the visual space, which is called visual servoing in the literature. So this is an example of grasping without this visual feedback on the hand using only the forward kinematics. And you see that this error is that I was describing before is too large for the robot to grasp an object successfully. So what we have done is to use the knowledge of the position of the hand in space using the kinematics, plus the knowledge of the shape of the hand using the CAD model of the hand itself. And the idea is that the robot can project in the images, it's sort of a mental image of the hand given a certain hypothesis of where the hand is, and then can compare this projection to the real images, and then can try to optimize an estimation of the position of the hand so that the mental image and the visual image match as close as possible. This in words, in practice, what we've done was to use a particle filter that is basically a system where you have several particles, each has an hypothesis of the position of the hand in space, and then each projects an estimation of the appearance of the hand in the camera, and then by using some features, you can compare each of these hypotheses against the real image of the hand, and then you can select only the particles that agree with the image and make them survive. And in time, after a short amount of time, only the particles that are matching are basically giving the correct hypothesis, and then you extract an estimation of the position of the hand in space. And this is now the same experiment I was showing before, but now you will see that when the robot moves the hand, there is this initial wrong guess, and then by optimizing the position of the hand using visual feedback, then you can have a good estimation where the hand is, and then using visual surveying, you can use you can pick a reference point in the hand and make it impact on a specific point in the images to zero the error, basically to control precisely the hand in space. And in this case, you can get a good grasp using only visual feedback because of the perfect knowledge or good knowledge of where the hand is. Okay, now the second part of my presentation is about objects, and in particular, learning about objects through touch. So now the idea here is that we don't have vision at this time. We only use tactile feedback, and the challenge here was to see if the robot could explore objects by pushing them, and by extracting the position of contact points on the objects through touch, estimate the shape of an object and build a model of the object, which is something that is not necessarily difficult to do if you have good tactile sensors that allow you to touch objects softly, but you need to have good position information of the hand in space. But then the other question is how many contact points do you need to model the object, and can you have a smart strategy that is driving you towards the points that are more interesting to reduce the number of touch that you need to do to actually explore the object. And this has been explored by people in different ways, and starting from the idea that how do we model this surface? Well, one way is to use an implicit function where you have you input an XY position, and then you get as an output the Z position of the height of the object. And this is a way to model the surface. So X and Y are your table, and then Z will be the height of the object, which is basically giving you, together with X and Y, it's giving you the surface of the object. But so you can model this with a neural network. People at the time were using Gaussian processes because they also give you uncertainty together with the output of the model. And the idea there was to use the uncertainty to guide the exploration in a sort of active way to try to remove to reduce the number of points. So the idea was to train a Gaussian process regression to predict the Z coordinate of the surface of the object, starting from the X and Y coordinates. And then the question was how to pick points. You can either sample uniformly or use the uncertainty from the Gaussian process. What we have done was to use a mix where we use Gaussian processes, but we also modified a bit the system so that we can reduce the number of points and drive integrate the exploration towards some areas of the object. This is what you get if you try to optimize only the uncertainty. In the end, you end up with a sort of a uniform sampling of the space, which is not optimal. And the reason is that the Gaussian process initially drive you towards the points that are more uncertain, but then as you get more points, the uncertainty moves, and then you end up basically exploring the whole space uniformly. Then what we propose is basically a different strategy. Instead of considering a function approximation problem, we considered a classification problem. So now in this case, instead of modeling Z as a function of X and Y, we model the probability that the object is present or not, given the 3 coordinates, X, Y, and Z. And this changes the problem in a way that can help to get an active strategy, because now the function that you get can be assumed as an estimation of the uncertainty of the border of the object. So if you search for zeros in this function, you're basically moving towards the object boundary, and you can see it from this sketch here. So suppose you have now the object simplified here. You take 2 points. This is random initially. You feed them to a classifier that tries to learn whether there is an object or not. Because you have only 2 points, you make a mistake. The boundary is somewhere here. Now you search for the 0 in these points, and you move to sample that point. So you go on that point and you get another point which will be on the object. Then you re-approximate the classification function, and then you search for 0 again. You get another point here. You get another point on the object, and then you see that my boundary here is moving in a way that is now closer to the actual boundary of the object, and to get out of the local minima. Otherwise, you will be still exploring this area. You move in a random way, you get another point, and then you update your classifier and get a better estimation of the object shape. So by using this strategy, we managed to have same exploration, but now guided by this active strategy. You see that points that we extracted were less uniform and more closer to the shape, to the borders of the objects, instead of moving on all points, especially on the table, which are not actually points that are useful. And here you see a comparison with the Gaussian process regression or the active strategy. And if you try to estimate the error in estimating the shape, the overall shape, you see that the error converges faster with the active strategy than with this random or the Gaussian process regression, which shows that the active strategy is actually beneficial to reduce the number of points that you need to get a rough estimation of the shape, or to improve it in time. Okay, so another way of learning about objects is, instead of pushing them, is by manipulating them. And this shows another behavior that we implemented. This is again blind object recognition. It's not shape modeling. And the idea is that you can give an object to the robot, and then the robot can manipulate it, and then extracting tactile features or the shape of the hand while it's touching the object can recognize the object. Okay. And this shows the behavior after the learning. And the idea is that then the robot is able to recognize these objects just by touching them. And this is actually after the training and shows the result. So several different objects here are given to the robot, and the robot is recognizing them by assigning labels that are not meaningful. So if it says red object or blue ball, doesn't mean that has any notion about the color. It's just the label that we gave to the object. But you will see that it does a good job of discriminating objects that are different in shape. And some objects are also ambiguous in terms of the size, but because we will see how it works, because of the manipulation, then the type of features that the robot is able to extract are also able to discriminate objects that are similar in shape, but they have different consistency. So how did we do this? Basically, this is very important, I think. I like this experiment very much because it shows how by having a controlled exploration of the object, you can simplify the recognition problem. So the strategy is like this: you put an object in the hand, then the robot has a controller that is able to reposition the object in the hands. I didn't explain how this works, but it's using tactile feedback to reposition the fingers, and then it's squeezing the object a little by increasing the pressure, and then it's moving all the fingers to touch the objects to get more points, as many points as possible. Now, through this exploration, you can extract different type of information. For example, you can extract at this point here the position of the joints of the fingers given the angles of the phalanges. You can get the same type of information in C after squeezing, and in D you can get the same information now from the whole hand, and you can also get a tactile response, for example, at this point here, C. All these are different features that can be combined together in a single classifier. And the way we did it was simply by stacking them into a single feature vector and then fed it to a classifier. And then the classifier was trained to recognize the object. Now, what was interesting is that these are all the objects that we tested, and you can get almost perfect recognition rate by combining all the information that I described before in the single classifier. But if you use only partial information, then you see that you don't get the same performance, which means that all these different type of interaction, they each extract information that is useful for the classifier to learn. But the other part that is interesting to me is that if you compare with a different strategy where the robot is not controlled in a precise way, but it's just touching the object without tactile feedback and then moving all the fingers on the object, but it's not repositioning the object carefully. And you get the same information, you extract the same type of features, then the performance of the classification is much lower, which means that the type of data you extract is much more noisier. And then the classifier has a much harder work to perform the classification. So which basically means that if you interact with the environment in a structured way, the type of data you can get is much better, and then you need either much less data, or you can do a much better job at whatever you're trying to do. For example, in this case, recognizing an object. But you need to have some controlled interaction, not completely random. And then we also did other experiments here. I don't show numerical results, but we did similar work where instead of just touching the objects were also rotated, like in this case, rotation or lifting of the object up and down. And this was to extract more meaningful information about the dynamics of the object, for example. And all these different exploratory strategies were combined together to recognize the objects in a better way. Again, the type of interaction that you can get with the object is fundamental to get better data and to simplify the problem of recognition. Okay, so the last part of my talk now is about learning about objects through vision. And now here the problem that we addressed was where to get the supervision. So if you look at the literature on machine learning, vision is typically solved by getting data sets that have been previously labeled by a large amount of people or with large amount of effort. Now, what we wanted to implement were strategies that allow the robot to learn alone or with the help of a human teacher, but without resorting to manually annotated data sets. And so here the problem we addressed were three. One was how to learn from a human teacher and learn fast enough so that what you learn can be used in a short amount of time without waiting hours of computation. And then another problem was how to learn new objects or better objects, improve performance on recognition without any human supervision, just by active learning, using previously acquired knowledge from a human teacher, but then now autonomously how to transfer that knowledge to new objects, which is the second part that you see here. And this is a problem because when you learn objects in a certain condition, there is a bias in the data set you acquire. So there is a drop in performance if you learn objects, like in this case, in an in-hand demonstration, and then the same objects are put on the table. So there is a drop of performance, and then the question was, can the robot learn by himself how to fill this gap without resorting again to human supervision? So for learning with teachers, what we have done was to solve some problems to give the robot the ability to first recognize the teacher himself among different humans, and then also how to establish the interaction. For that, we used mutual gaze, eye contact. And then the other part was where to look at, where is the object that the teacher is showing to the robot. And for that, we used gaze direction. So we assume that the object is in the hand. The robot has information about the position of the hands, but he doesn't know which hand to look at because he doesn't know about the object. He's not able to recognize the object yet. So for him, the object doesn't exist. So by using the gaze direction, we can focus the attention of the robot either on the right or on the left hand, and then this can bootstrap the learning. So here you see the whole system. Without going into details, we have speech recognition that is used to get verbal commands from the teacher. The teacher will tell the iCub, this is a mug, for example. Then we have a teacher recognition system with vision that is recognizing the specific person that is the teacher, selecting the hand, and then going through the images, looking at the hand for extracting the blob, an area around the hand as a training sample. And then this goes into an online object detection system that is learning the object. And the mutual gaze is activating the speech recognition so that the robot is not listening to all the speech, all the noise in the environment, but is only turning on the microphone when there is mutual gaze. For face recognition, nothing super special. We use the FaceNet, which is a neural network that is already available off the shelf. Then using OpenPose, which is a system for getting the pose open up for a person in the images. We extract the face, and then we extract examples, and we train a simple supervector machine to recognize the person as the teacher.
I am the teacher.
So this is how this works. This is now the phase where the robot is getting examples, frames from the head of the teacher, and after the demonstration, then the machine learning algorithm, the supervector machine is trained, and after 6 seconds, the robot now is able to assign the label teacher to the person that is in front. Then the second part was to detect the gaze and the direction of the gaze with respect to the hand. So just the left and right was sufficient for us at the moment. With the way we train this system now is again using open pose. We extract all the points that are characterizing the skeleton of the person and also the face. And again, we classify we use two binary classifiers, one to detect when the eye there is eye contact, and the other one when the person is looking on the right or on the left. Yeah, this was actually done with a data set that was acquired separately, not on the fly on the robot. And this shows the mutual gaze. You see that the person is now looking up and down. MG no on the image means there is no mutual gaze, and then you will see that when it says yes, it means that the person is looking at the robot. And here is detection of left or right to know if the person is looking on the right or on the left. And this is the whole system together.
Have a look at this mustard.
When now the person, Elisa, is teaching the robot to look at the mustard, and Elisa has been trained as the teacher, so the robot is looking at the hand of Elisa. Elisa was looking at her right hand, so the robot is looking at the right hand, and there is another person that is trying to fool the system, but you saw that the robot was only looking at the mustard that was in the hand of Elisa. And this is now an example of the actual images that are acquired from the cameras that are now becoming part of the training set for the robot. And now the other part that we worked on is on making the system fast enough so that during the demonstration, almost in real time, the robot can learn new objects without wasting hours of training offline. And to do that, we worked on the deep neural network, and we did a couple of things that allowed us to reduce a lot of the training time. The first part was to remove some of the layers of the neural network and use, again, kernel methods. And in particular, we use a kernel method that is efficient. It is developed especially to be fast. And this allows us to remove some part of the neural network of the network that is required to be adapted when the system is learning new objects. So the idea is that you have a system that has been trained on a feature task, so using a data set or general purpose data set. But then when you have to train new object, you need to modify some part of the network, which are the one in red. And if you use conventional network, it takes a bit more time. If you use our method, because we use special kernel methods here, it's faster. But the other part that was required, we observed that during the data acquisition, when the robot is looking at the objects, there is a long time that the robot spends looking at objects just to acquire the training samples. And that is lost unless you can do already some processing during that part, during the exploration. So we try to modify the training protocol so that during the exploration, the robot could already do some part of the computation, which was then not necessary afterwards. And to do that, we needed to modify how the system was trained. Normally, the system is trained by first extracting features from these convolutional layers here. Then you train this initial part that is a region proposal network. So it's just telling the system where objects are likely to be. And then you pass again through the network and you extract features that are now sent to the last layers that out of all these candidates are assigning labels and is also selecting, segmenting the object by cutting exactly the contours of the objects. And then finally you can train the last part. But in this process, what you do is you extract the features, you train one area, then you extract again the features, and then you train the second layers. which is not possible in real time. You need to do it while you do the training. In our case, what we have done was to extract features once using the region proposal network, the original one, and then in one shot retrain the whole system, all the 3 components, without extracting features again. If you do this, then it means that you do only the feature extraction, and then separately you do the training. And this allows us to do this feature extraction while the robot is looking at the objects. And then after the demonstration, we just need to retrain these 3 parts. And this allows us to keep a lot of time, to save time, and to reduce the training time. And this is a comparison with the state of the art and the performance we get with our method, which are not the top you can get with the full retraining, because our system is approximated. But if you are in a short amount of, if you have low budget in time, you can get almost the performance that you will get with the full training, but in much shorter amount of time. And this can be useful for the robot to learn in real time without waiting long training times. And this is a comparison qualitative on the given a certain budget and time, suppose 20 seconds of training, the type of performance you can get in with our algorithm or with a full training of the system. That is still giving you a nice result, but you see that there are more errors here because the performance are lower. And these are 2 different data sets. But what is more interesting is what you get on the robot, and this finally is closing the loop. We saw how to extract the hand, the teacher, and now this will show how the robot learns the object after the demonstration. So here is acquiring training samples, is already extracting the features, and then after the demonstration in a couple of seconds is able to recognize this new object. And the idea is that you can teach the iCub to recognize other objects if needed. In the same way, you can keep going and you can show new objects and have the robot learn them. Or if the robot is making mistakes, you can correct him and retrain a new object, or retrain an object that was already known in the past to increase the performance, a sort of continuous loop. Okay, I have also some other slides, but I don't know if...
Yes, you can. Yes, you have the time, because I told people that they could interrupt you with questions at any time. That means you have the time.
Okay, so I can keep going. Okay, so yeah, what I mentioned before is, suppose you have this method where you teach the robot new objects, then objects are now in different setting, and unfortunately, the performance are not exactly the same. So there is a bias, as it is called in the literature, that is introduced by the specific way in which you show objects to the robot. For example, the hand in the in-hand condition. And then when you put the objects on the table, there is also different lighting, different background. The performance have a drop. So the question was, should we retrain the full system, or can the robot learn something by itself, or mixing some help from a human and some self-supervision? So what is the idea is, suppose now you have objects on the table, the robot can look around and look at the objects, and then using previous knowledge, it tries to recognize objects on the table, and there will be some areas where is certain that the objects are actually there, and some areas where there is an hypothesis, but these areas are not very super certain. Now the question is how you know if some are certain or not. But suppose you can guess them, which of these recognition here are the good ones, then you can extract the ones that are strong, like in this case, suppose these are the strong ones where the system is certain, then this can become new training samples. So the robot attempts to recognize objects, fails in some cases, but is able to know where it's failing and where it's not. And then you can use the labels where he didn't fail as new training samples. And this basically, it's a loop where the robots, starting from an initial demonstration that was in hand, looking at new objects in a new context, can extract new training samples and then feed them back in the original data set, retrain the system, and improve the performance. Now, the tricky part here is how to detect which of these predictions are good and which are not. And this is actually the trick. What you can do is, instead of discarding the ones that are not certain, that are wrong, you can ask to a human to label them. You can say, look, I'm uncertain about these two objects. Can you tell me the name? And then if the human teacher gives it the name to the robot, then you can also use those are good training samples and feed them in the training loop. Now, the way to do this is how to know which label is good and which one is not. That is a very simple way. You take the bounding box of the object that is candidate to be recognized, and you cut it out of the image, and you paste it into a new image. And then you look if the recognition is consistent across different different images. So you can paste it across in different backgrounds, and then you can look if the classification is consistent. If the classification is consistent, you assume that recognition was good. If the classification is changing, that you say, okay, that label was not very good. I need to ask the teacher to classify it for me. And this is how it works. Again, this is an initial demonstration. You, as before, training the objects. But now, after the training, these objects are placed on the table and the robot is looking at them. And you will see that the performance are not super good. Some objects are missed, sometimes are flickering. So that means that the recognition was not super successful for that specific region. Now, what you can do is you can do the exploration, and then you can apply the method that I described before. In this case, these were the labels that were detected as uncertain. The robot asked the human to label them, and then from now on, it was just exploring and getting data autonomously, and then feeding them back into the training system. And you see the refinement model after this process in contrast to the original model. And you see that the refined model is more reliable, is able to detect all the objects and more consistent across in time, whereas the original model was failing much more. And what basically numerically, we have run an experiments where we compared the performance before the refinement process and after the refinement process, and you see the increase in performance that you get and the number of images that you need to annotate using the human, which are only 4, 3 images or 5 images at most, instead of manually annotating a full sequence. So by just giving the robot a few examples, then the rest is automatically extracted by the robot in a sort of self. Yes.
Can I ask a methodological or a motivational question about this parameter? You made a distinction with the stuff that you presented in the beginning between feedback from consequences, nothing to do with human labeling, just consequences of doing things this way or that way, or sampling this or sampling that. And then you switched to consequences from what used to be, what in a non-robotic situation is coming from labeling. And so you had a teacher who was basically, in this last example, it's clear, you were even getting feedback from a teacher on which of the prior strategies worked or didn't. Now, could you just explain to me either the methodological or the motivational reason for this variable? Which is a variable that, maybe my question is, if you had instead of taking the robot that has to name these objects, for example,
Yeah.
if you had simply had geometric shapes that that were different, but many instances of geometric shapes, then it would have been learning the geometric shapes without the label, without the human teacher. What is the function in your research program of this human teacher component?
So you need the teacher to give the name, which is probably not fundamental because the name can be anything, but you will still need to give the bounding box. You need a way to extract where the object is, which you could also do with geometrical features, but it becomes very tricky if you have a clustered environment, because you may have different objects, one on top of the other. So getting the background, foreground segmentation, it is something that is difficult to do. And the human is basically giving that for free by moving the object, for example, with motion is segmentation, or by showing the object in a very specific way.
I understand that doing it improves performance. There's no question that it does. But my question was about motivation. What are you trying to beat benchmarks? We sort of get better performance than benchmarks, no matter how the benchmarks were achieved, and no matter how you achieve them, you want to better them. That's one motivation, and that's legitimate. Mm-hmm. Are there particular applications where it makes sense to talk about intervention from teachers in the
Yeah.
learning, or is it ecological, which is
No, I think it's practical. So we assume that robots will be interacting with per people, and so having this interaction could be actually an application where suppose you have a robot at home and is able to recognize already some objects that have been pre-given by the developer, and then you need to add new objects because it's a object might be something that you only, a specific object that you only you have, or there is a failure in the system and that particular object is not well recognized, then having a loop where you can teach the robot that specific object can be beneficial in practice.
So it's motivated by a specific kind or family of applications.
Yes.
Okay. Yeah, the reason I ask is not because I have anything to criticize about specific applications, but I think this stuff is potentially much more general and powerful, what you're doing, than to channel it towards a specific application. It would be interesting, for example, to hear with the methods as you describe how a completely bottom-up, how far could a completely bottom-up approach get?
Yeah. No, it's true.
Okay, sorry to interrupt you. What about you?
No, it's actually a good. It's actually good. It's actually a very interesting question. Yes, yes, I agree.
Okay, but go ahead, please.
Okay, so the other similar work here is now the robot is exploring by navigating, and in this case, is actually not using human supervision. So maybe this is closer to what you are suggesting. This is still a work in progress. Is in a virtual environment, and now what the robot is doing is from pre-acquired knowledge is projecting what it can recognize on the objects in the environment, and then is building a coherence map by looking in space if all the recognitions that it's able to do of the object recognition are coherent or not. If they are coherent, it means that that object specifically is okay, but if they are not coherent, it means that that area is interesting, and then it can explore it more, and then tries to solve the incoherence by looking at the maximum of a sort of where multiple classifications are in agreement, and if there is a sort of maximum voting of the labels, is then retraining the system again. So it's similar to what I showed before, but instead of having a human teacher, the robot is solving ambiguity autonomously, and then is navigating. Here is exploring the environment to maximize the incoherence between the labels. So it's looking at, it's going exactly, it tries to go to explore areas where his visual system is more uncertain, and that is getting better better data, because basically it's a sort of curiosity in a way for the robot to explore. So this basically allows us to increase again the performance out of an initial performance of the pre-trained system to the performance after the self-training and the exploration. Yeah, so this other work instead is this is no longer about learning objects, it's more about tracking them. And here what we wanted to solve was tracking objects, the position of objects in space when they move. And the challenge is that when objects move, you need to be very fast. Otherwise, you have the lag, latency, and the latency is bad because you don't get a good estimation. Now, the way we solved it was by using convolutional neural networks, but the problem is with convolutional neural networks is that they are sometimes slow, especially if you don't have super powerful computation. And the idea is that we combine that information with optical flow that is very fast and easy to compute. So the idea is to have three sources of information. One is a neural network that is segmenting the object in the images. Another one that is providing an estimation with the pose of the object, and then the optical flow is giving an estimation of how the object is moving. And the optical flow is super fast, so it can feel the lag between the other two estimations. And by using a Kalman filter, we estimate the pose at high frequency, and you see the performance of our system when we have object moving. You see that in our case, we managed to follow the object closer while it's moving, whereas other systems in the state of the art, they have time tracking the object, they get lost or they lag behind. And this is also beneficial if you have objects that are occluded, because by using the fact that you have sort of a time evolution of the pose, you can deal better with the occlusions, because the object there is notion that the object cannot jump away, but has to be sort of in the same place or moving slowly in space. I think the last part is again using vision, but a bit more on where instead of what. So where are objects and how I can grasp them. And here the problem is how to estimate the shape of an object by looking at a partial view. So you see an example. This is what the robot sees when it's looking at an object. And because it's seeing the object from one side, it doesn't know what it is behind. If you don't do anything smart, then if you say this is just an estimation of grasping points with a gripper, the system might think that there are areas where it can grasp the object that don't exist in practice, just because the view of the object is partial. And we have done work to solve this problem. One way was to assume symmetry of objects and using elementary shapes, in particular a form of function that is called superquadrics, that are three-dimensional extensions of circles and ellipsoids. And they can represent families of objects that you see here, boxes and cylinders, by a few parameters. Then you can basically fit from a partial view of the object you can fit this shape and you can have an estimation, a rough estimation of the size and shape of the object that you can use for planning how to grasp the object. And you see here an example that there is an object here, is a cylinder, and then the robot has estimated the shape and then is controlling the hand to go. And you can put the fingers on the back of the object because by assuming symmetry, it has a notion of the shape that is three-dimensional and it's not just getting fooled by the fact that there is an occlusion. But then the question was, can we do better? And this has been done also by other people. Again, using neural network, what you can do is you can train a neural network to provide a full estimation of the shape of an object starting from a partial view. And this is called shape completion in the literature. And it can be in fact used exactly to solve that problem. And because the neural network can embed knowledge about objects, then can do a better job at guessing the shape of an object by looking at the partial view, because it has sort of embedded information through hundreds of examples. And in this case, what we used was a data set for grasping and another data set that is using robotics. We have 3D shapes in this case, and by generating several views, partial views of the object, knowing what was the original shape, we trained the neural network. I don't go into details, but basically it's a two-system, it's a two neural network system. One is feeding the weights of another neural network. So there is a convolutional neural network with an attention system that is getting the partial point cloud and is providing the weights to another neural network. And this neural network is approximating the shape of the specific object. And then you can sample the space with a set of points, and then the neural network can provide the reconstruction of the shape. And the idea is that this initial neural network can be, by recognizing the object, can provide better shapes for the other neural network to complete the shape itself. And you see here some examples of objects, different objects, and the way they have been completed. The other thing that you can get is out of this network an estimation of the uncertainty again. So here the color coding is different if the object, if the network is more certain about the point, it's yellow. If it is uncertain, it's blue. And this is naturally coming from the fact that these yellow points are actually from the surface of the part of the image that are visible, whereas the other part are hidden, so there is higher uncertainty. But it could also be due to the specific shape of the object, and there could be areas where it's more uncertain. And this can be important for grasping because it can guide the fingers of the robot towards areas where there is higher reliability of the estimation of the shape. And this final video shows what you can do by, again, you see here, this is now a manipulator, an industrial manipulator looking at an object. There was a partial view of the object and then was completed by the neural network. And then after that, the robot is planning the grasp for picking up the object using the reconstructed shape and instead of the partial one. And how it is beneficial is demonstrated in this video here. Exactly in this case, the object was estimated, the full shape was estimated, but if you don't have the full shape, the system might get fooled and go to grasp the object in the red areas. But what we want is to consider the green areas that were showing before, the actual borders of the object where the gripper can go and pick up the object. Now, because we use the full reconstructed shape, you see that the planner, the algorithm that is computing where to put the gripper, has selected areas on the border and is actually picking up the object from the border instead of from the other areas that were sort of artifact due to the partial view. And yeah, this was my last example, my last experiment, and this is my group, and I just want to acknowledge all the people that have done the work that I presented, and also the funding from European projects and IIT itself and INAIL, which is the worker insurance agency in Italy that has funded some of the work that I presented. So
Thank
you very much.